So we determined the dynamical equation for the probability density, and we said that this is going to be I del dot. This is the Liouville operator. And the solution to this equation is e to the power minus L hat n times t rho of xn comma 0. We also saw that if we set the left hand side to 0, so that rho of xn comma t goes to just as a function of the phase space variables, this would essentially imply that rho of xn must depend only on the energy, where your energy, total energy, is given by the Hamiltonian, which is a function of xn. Now we have been saying that in the phase space, which is this inequality, let's say, so when you allow all energies greater than equal to 0, less than equal to E, then E defines this surface and you have a volume contained within this surface, right? And we said that in this, when we developed this picture of probability density, classical probability density, we said that imagine that this phase space is now filled with continuum fluid of state points. This fluid is made up of state points, and this flow is essentially governed by the Hamiltonian dynamics, and the fluid of continuum fluid of state points that you are visualizing, that you are imagining, is essentially an incompressible fluid. But how do we see that this is an incompressible fluid? So the probability flow within this volume is similar, or is exactly the same as a probability, as a flow of an incompressible fluid. In an incompressible fluid, the volume element does not change, right? So which means that, let's say, if I look at the volume element d of xn at a time t, I have a Jacobian that connects it to the volume element d of xn at t0, right? So if you imagine two time snapshots, one at t0, the other one at t, and then if you consider a volume element in the phase space which has denoted by t0, then this volume element will go to the volume element dxn at the time t. So the question and the relation between these two volume elements are given by this, where J is the Jacobian, which takes you from t0 to t. So J of t comma t0, I'm sure you have learned Jacobians, is Pn t0 q, sorry, this has to be. So note that, okay, if you, let's take one step backward, and we want to, so the volume element over here is d of Pn t0, d of Qn t0, and the volume element over here is d of Pn t, d of Qn t, correct? So essentially there's a transformation that is involved over here, which means that Pn t0 goes to, well, we'll not say d, we'll say Pn t0 goes to Pn of t, and Qn of t0 goes to Qn of t, right? So this is a transformation, and therefore I can write down the the Jacobian for this. This is going to be and similarly you will have Qn of t del Pn t0 del Qn t of del Qn t0. It's exactly the same thing that we have defined earlier when we did thermodynamics, if you recall. So this is the Jacobian is the determinant of this matrix. But let's write down the equation for P and T plus right, and Qn of T is Qn of T0 plus Q dot of N T0 delta T, plus of course you have higher order terms, which is delta T square over here, right? Now let's look at this derivative now, right? If I look at this derivative, then del Pn T del of Pn T0 is 1 plus del P dot N T0 del Pn T0 times delta T plus order delta T square. Similarly, N T0 is del P dot N del Qn T0 delta T plus higher order terms, right? One can do it for the Qnt also. So del Qnt del Qn T0 is going to be 1 plus del Qn dot T0 del Qn T0. So there is no dot here, so one has to be careful. Delta T plus order delta T squared term. So once we have this, and therefore one can also write down the corresponding term for del Qn T del Pn T0, right? So if I now, using this form of the Jacobian, using the Hamilton's equation of motion, what I should have is del Pn T0 del dot del Pn T0 delta T. We'll ignore the higher order terms over here, and this one is going to be 1 plus del Qn dot del Qn, both evaluated at T0. This quantity is going to be del Pn dot T0 del Qn T0 times delta T, and this is going to be del Qn dot del Pn. Oops, the n has now come as a subscript, T0 T0 delta T, correct? So 1 plus del Qn dot, del Pn T0 del Pn T0 plus del Q dot N T0 del Qn T0. There are higher order terms which we will not consider. So if you just consider this times this, then this is going to give you this result, right? But we did this. This is equal to 0. So therefore, J of T comma T0 is 1 plus order delta T square. There is no delta T term that survives this equation. So one can therefore write down J of T comma 0, the Jacobian. You start from time 0 to time T is J comma T comma T0, J comma T0 comma 0, right? So this becomes J of T0 comma 0 1 plus order delta T square. So dj dt is equal to limit of delta t to 0 j comma minus which is going to be 0, right? Therefore, it follows that dj dt is equal to, dj dt is going to be 0, which would imply that d of xn comma t is going to be d of xn comma 0. Therefore, the volume at this volume element that you considered at t equal to t naught and at t equal to t are the same. So the volume is preserved. The flow of probability, and this essentially is another statement that this is a conservation of probability, therefore the probability cannot be lost, it does not leak out of the volume, therefore this flow of probability is essentially an incompressible flow, which means that there is no loss in probability. So we looked at the probability, n particle probability density, and we said that this equation, the dynamical equation for the evolution of this, obeys the Liouville equation of motion, is essentially the Liouville's equation of motion. The solution to this equation is, there has to be an I here, e to the power I L hat n times t rho xn of 0, right? Further, we established a little while ago that the flow, probability flow, is incompressible, which essentially means that there is no loss in probability, right? So how does one visualize this? You can imagine that there is a hypersurface which is defined by this conservation of energy in the 6n dimensional phase space. So I can imagine that there is a hypersurface which is defined as by this equation with the right hand side. E is a constant. Now I can consider a small patch which will denote the initial conditions of all my particles, right? And as the system evolves, this patch slowly and slowly evolves throughout the phase space, because there are several trajectories. This is when, if you wait sufficiently long enough, it encompasses the whole of the phase space. It's like a spreading of an ink drop in a liquid. The Liouville equation has several properties. Number one is, this obeys the time reversal symmetry, because the underlying macroscopic dynamics obeys the Hamiltonian equation of motion, which is time reversal. Therefore, this equation obeys time reversal symmetry, right? It's a Hermitian, the Liouville operator is a Hermitian operator, and if you look at the nature of the solution, particularly this term, this essentially tells you that the solution is always oscillatory in nature. Therefore, one must understand that this equation does not describe the irreversible decay of the system to a unique equilibrium state. So one must start off with the equilibrium state from the very beginning itself. So as time evolves, in this picture that we have tried to establish, that this is an incompressible flow, in the phase space, and therefore if you start off with a small patch of initial conditions, it's going to evolve as time progresses. the trajectories are going to evolve so that it slowly and slowly covers the whole of this phase space, right? Now, what does this mean? So, is this always guaranteed, right? That is the point that which we want to discuss. Now, before we try to discuss the consequence of what we just described, that if you start off from a small patch of initial conditions, it slowly, as the time evolves, if you wait sufficiently long enough time, there's a randomness already inbuilt, because in this initial conditions, therefore, the whole thing covers the whole of the phase space. And what is the consequence of that before we describe that? So I want to just write down what we are mainly interested in. We are interested in typically our expectation values of dynamical variables, right? And say A of xn, right? Well, not xn. We are typically going to be interested in dynamical variables A of t, right? Then the average of A of t is defined as d of xn. This is the measure. A of xn, rho of xn, comma t, right? Which is going to be d of xn, A of xn, e to the power minus I So this is kind of the Schrodinger picture where the operator does not carry the time evolution, but it's the probability density which carries the time evolution. We can write down alternatively the same expression for average of this, which is the Heisenberg picture, where I'm going to have I'm going to take this term, which becomes d of xn, A of xn, comma t, where now this dynamical variable obeys an evolution equation which is L hat n. Sorry, just being a little bit clumsy. A of xn, comma t, right? Anyway, this is just as a remark that one should remember, but we are mainly interested in an equation of this form where I define the expectation of a dynamical variable in terms of the probability density. Now, coming back to the original question that we posed, that with the picture that we have developed for rho of x and t, we realize that first of all, this vector is, the tip of this vector is essentially bound to move on this surface, which is defined by the conservation of energy, right? Such surfaces are what are called isolating integrals. So for an n particle system, this is the only isolating integral that we can have. So in the phase space, an isolating integral would consist of a closed surface. There are other type of integrals which are called non-isolating integrals. So your conservation, your constants of motion, your conservation of momentum, conservation of angular momentum, and your conservation of energy, of these, only this one forms the isolating integral. And this is therefore very, very important in what we are going to discuss. Now clearly, let's draw this thing a little bit over here. I have this surface which I have again, let us just write down this as this. And as I said, that as the system evolves, it slowly and slowly fills up the whole of the phase space, right? So what does it mean for us? We cannot observe these quantities, right? We cannot observe x of n experimentally. We are rather interested in a limited set of dynamical variables, A of t. It can be the total energy, it can be the total momentum, whatever that is. We are only limited to observing this. Now, as we have said that clearly this is one possible way of defining the expectation value. There is yet an alternative way of defining this expectation value, which would say that if I have the time series of A, which means I measure A as a function of time, then I can define that a different average, with limit of t2, capital T to infinity. So essentially this means that you measure this quantity for a large time window and essentially you calculate the average, and this is going to be another average which you'll write down A of t. This average, so here it is no longer a function of t, but it's just this. This average is defined in terms of your phase space. Why? Because you are using the phase space density over here, and this is purely a time average. Right? Now the question is this equal to the phase space average? Right? So now that we have two averages that is defined, one is the time average, average A of t, and the other one is the phase space average. The question is whether both of these are equal, and when are they equal? And the answer to that comes from the Ergodic theorem. The Ergodic theorem essentially tells you that not only that the time average should exist, but if the system is ergodic, then the two averages are equal. So this happens when the system is ergodic, or alternatively the flow in the phase space is an ergodic flow. There are two kinds of flow generally which is considered in a phase space, which is but we'll not worry about that right now. So our point is that if the flow is ergodic, then the time average and the phase space average are equal. But what does this mean? Let's go back to the picture where we were visualizing the phase space, and our phase space trajectories had all covered up the phase space. Now if you consider a small region R as indicated over here by the black closed surface, and you ask that what is the probability that the state, which is denoted by xn, is in this region R, then since the whole of the phase space is completely filled, therefore the answer to that question is essentially that probability, let's say, is equal to sigma R divided by sigma E, where sigma R is the surface area contained by this black content within R, and sigma E is the total surface area. Sigma E is formally defined as d of xn delta of hn xn minus E. So essentially the delta function guarantees that the tip of this vector, measure is only takes into account the surface area contained within this volume, right? Now since the flow is ergodic, the time average is equal to the phase space average. Therefore this probability also means that this is equal to the time that the system spends in this region R to the total observation time. So when the flow is ergodic, in equal areas in the phase space, the system will spend equal amount of time. If there are no isolating integrals for an n-particle system, if there are no isolating integrals other than the conservation of energy, then the flow is ergodic. There can be other isolating integrals, and for any n-particle system, there can be other isolating integrals other than the conservation of energy. And finding the number of isolating integrals is really a very difficult job. Right? Now let's come back to this expression. So once I have this probability, then you see this probability I can write down as 1 over sigma E integral dx, sorry, not dxn, but essentially an integral over the surface area in the region R, right? You can write down in terms of xn, but you have to also include delta hn minus xn, and the integral is over the region R, right? Now, if you recall when we discussed continuous random variables and probability densities, we said that the probability of finding a variable x within a range or within an interval R was essentially over the interval dx and rho x, right? And surprisingly, if we just look at these two, then this has a similar form, and we immediately read off that rho of xn is 1 over sigma e, where sigma e is the surface area and defined by the isolating integral h of xn is equal to e. This simple looking expression that we have come to essentially tells you that all the points in the phase space are equally likely to be visited. It is also the point to be noted is that this expression does not contain time anymore, because we have waited sufficiently long enough for the system to evolve so that the phase space is completely filled, and we have therefore reached a stationary state. Correct? This equation is what is called a microcanonical ensemble, and the average of any dynamical variable is now dxn axn delta hn xn minus e 1 over sigma e. The delta function once again ensures that it's a surface which is only matters here and not the volume. We shall get rid of this. We shall see later on how to get around this difficulty. Correct? It is also worth noting that when we visualize this picture over here of the phase space, we said there is no other, when we visualize this picture, essentially this also means that there are no other interactions present in the system. So you do not have, you just have your system. There is nothing else. So therefore, this would correspond to an isolated system, what we consider in thermodynamics, right? An isolated system in thermodynamics essentially means a microcanonical ensemble in terms of probability or statistics or statistical mechanics for that sake. Good. So now that we have this probability density, what do we want to do? The bridge is given by the statistical entropy, or we will just write down entropy S as minus sum over Pj ln Pj, except now we have minus integral dxn rho xn ln rho of xn divided by Cn. But clearly what we are interpreting as entropy does not have the dimension of entropy. So what we introduce is a Boltzmann factor S, right? If we introduce sigma e, rho, if we use this expression for rho of xn is equal to 1 over sigma e, then you see your entropy is kb ln sigma e over Cn. Note the reason we have introduced a Cn factor over here is because this surface area is dimension full, because this surface area has dp1, dq1, dp2, dq2, so on and so forth, and we shall later on see what Cn is going to be. Now coming back to this, This quantity is called the structure function and is defined as d of xn delta of h of n xn minus e. And you can imagine that for a 6n dimensional space, it's a notoriously difficult quantity to evaluate. So what do we do? Well, we start off by saying that, look, instead of considering that the system is strictly at an energy level E, I can also consider a spread in the energy level so that I replace this by E plus delta E. If that is the case, then you can think then this surface area that we are considering is now replaced by the volume which is contained within this shell defined by En E plus delta E. So that I have now omega of delta E as a function of E as integral dxn over this region and your probability density rho of xn is just going to be omega delta E. So that your entropy is going to be Kb ln omega delta E over Cn. Right? If your delta E is small enough, this can be approximated by sigma E delta E, right? Not otherwise. We shall also remove this restriction on delta E. So now that we have replaced sigma by E by the volume which is contained within this shell of energy E and E plus delta E, even this volume is also very difficult to calculate. Before we go ahead with this argument that how we can replace this, what we want to say about 2 points is that this sigma E that we originally started off with, essentially that represents the surface area of the isolating, defined by the isolating integral, is also a measure of the total number of microstates of the system, right? What we have been calling xn as states are essentially the microstates of the system. And in principle, although we have been denoting it with by E, this for a hydrostatic system, for an n-particle system which physically occupy a certain volume in space and has certain particle number, is more explicitly written as sigma E over n, and so is omega delta E as E V n, right? So now what we want to look at is how do I replace this cumbersome calculation of the shell in the hypersurface by something more easier to do. For that again, we consider this inequality where now my system is allowed to have energies all the way from 0 to E. So essentially you define this hypersurface which is denoted over here, and the surface, the bounding surface, is defined by the energy E, whereas the system is allowed to have energies from 0 to E. What you now do is essentially you break up this volume into small shells of energy of width delta E. So let me just quickly try to schematically draw them. This is also delta E. Again, you have an inner. So you keep on doing it so that you have E over delta E number of shells. The outermost shell, which is contained between, so let's write here outermost shell, which is contained between E and E plus delta E, has the volume omega delta E, EVN. Why am I suddenly interested in this? Or because this is exactly the quantity we have been dealing with earlier. Therefore, if you look at it carefully, so this is the shaded volume that we are referring to. Now, the total volume omega EVN, which is contained by this hypersurface, is sum over I omega delta E, EI, comma V, comma N. But if you look at this expression, it's very, very evident, even this pictorial representation is very, very evident that this quantity, the total volume which is contained within this hypersurface, is definitely more than the shaded area, right? So therefore we can write down this as omega delta E, E, comma V, comma N is less than omega EV N. E over delta E number of shells. If I multiply this by delta E EVN, then the total volume is less than this volume, right? So now if you take a log omega delta E is less than ln omega is less than ln E over delta E plus ln omega delta E. Note that this is the one which enters the entropy, right? On the other hand, so this is the total number of microstates, log of that, and is therefore is an extensive quantity. In contrast, E is an extensive quantity, and therefore E over delta E would scale as N, whereas log of omega would scale as N. So if you now take the limit, the thermodynamic limit of N to infinity, large number of particles, then you see in this inequality, this term drops out of the computation, because this is only ln of the order of ln N, whereas this term is N, this term is N, this term is N. So what I mean to say is of the order of and this term is of the order of ln N. So this term drops out from this equation, and you have very nicely ln omega delta E is less than ln omega delta E, right? So that in the thermodynamic limit, the omega delta E, ln omega delta E, what we have been using in place of the entropy is ln omega EVN, the total volume contained within the phase space, right? So we rewrite our equation, our expression for entropy as Kb ln omega EVN divided by Cn. We shall come back to Cn, but right now it suffices to say that Cn is equal to h to the power 3n for distinguishable particles and is n factorial h to the power 3n for indistinguishable particles. H is the Planck's constant, and it's not very surprising to figure out why H comes in, because if you look at the measure in the phase space, it is d of xn. If you expand this, then this is dp1, dq1, dp2, dq2. So the product of P times Q has a dimension of action. Same quantity right, as h as the Planck's constant. So essentially, you non-dimensionalize this volume by h to the power 3n. The introduction of this h to the power 3n and the n factorial is clearly something which is done by hand in classical statistical mechanics. We have no way of introducing it very naturally in the theory. We shall see later on how quantum statistical mechanics does it.